No pressure. I'm Russ Doty with Red Hat. There were two technologies that I was considering discussing here, containers, but that's way too big for 5 minutes, and accelerators, which is interesting in several ways. Let me make 3 predictions about HPC systems. 1, they will be running Linux. 2, particularly going forward, they will be using accelerators in addition to traditional CPUs. And 3, the accelerators will be hard to use. So looking at the accelerators, we are nearing a new golden age of accelerators where we can expect a literal explosion of hardware innovation and of novel new approaches to solving a wide range of problems. These accelerators will tend to be domain specific. They will do one thing. Hopefully they will do it well. In many cases, the performance advantages will be so great that you'll be almost compelled to use them. Now, some of the challenges are small startup companies in particular developing these accelerators will have to do things a bit quick and dirty. So there will be, particularly in the early versions, particularly if you are an early stage user, a bit of hackery going on just to make the bloody thing work at all. This is not something that we really want to do in a production environment. I'd like to suggest that there are several things that you should be discussing with accelerator vendors. We believe that the basic problems are lighting up the hardware, downloading whatever firmware or other software is needed to run the accelerator, communicating with the accelerator, and then allowing applications to utilize the accelerator. We're, of course, strongly biased in the Linux community towards open source, so we believe that we'd, of course, like to have everything be fully open source, but we recognize that that's not in the best interest of the companies at all points to fully disclose all of their IP. Some of their IP will be valuable. Some of it is actually not worth protecting. What we'd like to suggest is that several core pieces of the accelerator should be available open source and, in fact, should be upstream. This includes the device driver with the ability to light up the hardware, the mechanisms, any mechanisms necessary to download operational software and firmware into the accelerator itself, and a user space environment for interacting with and communicating with the accelerator. There can be value-added libraries and other things for implementing the IP. Tool chains for developing things like FPGA bit streams are going to remain proprietary for the foreseeable future, but we really believe that the basic pieces for lighting up and running the accelerators need to be open source and need to be upstream, particularly when we start having multiple accelerators in the system. Now, the other piece of it is making it easier for applications to use the accelerators. And one of the biggest issues today is that it's necessary for the programmer to manually move data between the system and the accelerator. Manually moving the data and keeping it in sync is a significantly non-trivial problem. Several organizations are working with an upstream project called Heterogeneous Memory Management, which is designed to provide a flat address space between the CPU and the accelerator. This means that all of the data transfer is handled at the operating system level, and that the programmer simply works with the data in terms of the memory it occupies. So the actual movement of the data between the CPU and the accelerator is maintained by the operating system, including management of stale data. There are several companies participating in this. Red Hat and NVIDIA were originating and driving it. Several other companies are increasingly using this, and multiple companies utilizing it is necessary for it to be accepted upstream into the Linux kernel. So anyone who's involved with accelerators and application development using accelerators, I would encourage them to look at the Heterogeneous Memory Management project.
So next, let's hear from XtremeD, and we'd like to welcome them as our first sponsor from Japan.
I work with XtremeD. Just to put some contents into what I'm going to say, this is a Japanese startup company that deals with cloud computing. And the technology vision of the company is to make it in the contents of cloud computing, is to create an integrated system that will make it easy, simple to both access, configure, and manage the operation of getting into cloud computing. So to this end, there is one of I don't want to talk about products too much, but there is a platform created and built upon it basically with the three components. One is the client side, which is provides the kind of dashboard and configurator, billing, and all kind of information that can flow into it. And secondly, a platform. The platform could be a customized bare metal kind of platform that's built that the client can use, or access to a virtual system on top of the public clouds, which allows the hybrid access and so on. And the third component of this one would be the gateway, which involves both a way to access as well as the file system and I/O that configured with that. The company is started locally in Japan. It's moving to the United States. And basically the whole idea here is to provide the kind of an umbrella integrated system that will combine ease of use with flexibility. There is a lot more detail to it, and the best way to do it is to go look at the demo of how it's happening. But that's the idea behind the company and the technology that we are developing. I think I can stop with that one.
Great, thank you very much. And then next we have AMD.
Excellent. So I just wanted to spend a couple minutes talking about some of the innovations that AMD is working on to what we call innovating beyond Moore's Law. And as we know, process scaling is getting more and more challenging each generation. And so as a result of that, we're working on a series of technologies to continue the pace of innovation for processor design. When I say processors, I mean both CPUs and GPUs within those new constraints. So some of the areas that we focus on with integration, we've been a leader in multi-chip architectures for almost 10 years, as well as 2 and 2.5D and 3D packaging, and then some of the scalable fabric technology that we've been developing. So as multi-chip architectures have come to market, AMD's really been a leader here. Like I say, what you see kind of on the left is what a monolithic die looked like at the end of the last decade. Actually, early in this decade, we introduced our first multi-chip processor for the server market. We've now expanded that capability. Our current processor is a 4-die MCM, and the product that we're planning to bring to market later this year is a completely new way of developing multi-chip modules that we call a chiplet architecture, where we have different IPs, different technologies on different dies. So you have basically a heterogeneous die approach where you have two fundamentally different dies put on the same package together to deliver a new high-performance processor. And through the use of chiplets, this allows us to put more silicon in each processor, enabling us to have higher performance. It also enables us to optimize the IP that's in each processor. Historically, cores and caches and those types of technology have scaled really well with new manufacturing processes, but a lot of the I/O hasn't, right? Your memory controllers, your PCI Express interfaces, your coherent interconnects from processor to processor historically haven't scaled anywhere near as well. And so we're able to put the right IP and the right process by using this architecture. Also, this is going to enable us to rapidly innovate. What you'll see as we talk about our roadmap, not today and tomorrow, but as you hear more and more about our roadmap in the months and years ahead, we're going to be able to very rapidly innovate and introduce next generation processors in a very rapid way. Another area where we've been innovating for quite some time is in the memory hierarchy. And from the CPU side, we were the leader in bringing higher performance memory to market. We were the first to have a 4 memory channel processor. We were the first to have an 8 memory channel processor. We're continuing to innovate there. Also, within the memory subsystem of our processors, we've been a leader in security technologies. So we have technologies in our products today that enable you to fully encrypt all of the processor memory at line rate. So, like I said, full line rate encryption of the memory in our CPU processors. On the GPU side of the house, that's where we've been a leader in 2.5D memory stacking, HBM2. The products that we have in the market now have up to 1 terabyte per second of memory bandwidth there. And we're continuing to innovate and lead with 3D stacking technology. And that's an area within AMD's research and R&D areas where we continue to lead. The final area I wanted to talk about is the interconnects between our processors, both our CPU processors and our GPU processors. The technology that we have now, we call Infinity Fabric, that allows us to connect the CPUs together. We've also expanded that Infinity Fabric technology to our GPUs. And so with our current generation GPUs, you can coherently connect them together with this Infinity Fabric technology. In addition to leading in the coherency, we're also planning to have later this year the first PCI Express Gen 4 x86 processor. And then on the GPU side of the house, the product we introduced late last year was the first PCI Express Gen 4 GPU. So again, leading on speed and bandwidth and coherent and latency from a PCI Express standpoint. And from a AMD research standpoint, we're continuing to partner closely with both C6 and Gen Z so that we can have a future with coherent accelerators in an environment where the CPUs, accelerators, fabrics, IOs would all be able to share a coherent pool memory, and that's a technology that we're working on within AMD research. Thank you so much.
Great, thank you. And next we'll hear from Cray. Yeah, I'll get your slides up here in just a second. There you go.
All right. Good afternoon. I'm Brandon Drager with Cray, and today I'd like to talk to you a little bit more about the Shasta architecture. It's been in the news a little bit lately recently, so hopefully you guys have seen some of the recent announcements coming out of Oregon around the Aurora system that will be delivered in 2021 that will be based on the Shasta architecture that will be partnered to deliver with Intel. So when we first started many years ago, kind of looking ahead to what our customers would need for exascale, we really started to try to understand what are those workloads that they were going to be using, right? Because we talked a lot today, that future looks more and more like a converged set of workloads, increased usage of HPC, HPDA, and AI, machine learning, and deep learning methodologies. So when we first started off, we really need to think about the scale of that system, diversity of those workloads, and really one of the things that led us to was that for the interconnect, it really was going to require kind of a rethinking of what we were doing for HPC interconnect. So that first led us to the creation of what we call the slingshot interconnect, which you may have also been hearing about a little bit recently. The next thing that our customers told us about is that given the kind of the diversity of these workloads, that any future compute infrastructure really needed to have the flexibility to support kind of anything we could think of now and also in the future from a performance and power consumption profile. We wanted to come up with a very flexible compute architecture that could embrace all these different architectures over time and really enable researchers and users the choice and pairing the right capability with the right workload. The next piece, of course, was thinking about what was the storage environment going to look like. A lot of the feedback we heard from customers was, again, flexible, fast storage that would really kind of meet their needs for exascale. And then certainly not last but not least, the software environment really needed to have flexibility and extensibility to really kind of embrace innovation in the software that's going to continue to happen for many years to come and to be ready for that. So for Slingshot, we kind of started from the ground up, again, rethinking what this interconnect needed to look like. Some of the key things, again, we thought about were all these different workloads that we're going to need to operate, kind of peacefully coexist within the system infrastructure. So to do that, we really thought about what are the intelligent features that needed to be added to really enable that. So things like adaptive routing, quality of service, congestion management. A lot of these features have been present before in other fabrics, but we've got different approaches that we think are slightly novel that really enable kind of these workloads to really scale seamlessly. The other thing we wanted to think about too is where are these systems going to be built, right? So where are they going to be deployed? Data centers are going to be varying and different capabilities. Customers will also have existing, infrastructure they're going to use, for example, like existing storage infrastructure, et cetera. So we also designed the interconnect to be fully Ethernet compatible as well, and also has different packaging profiles as well, so both air-cooled and liquid-cooled, again, those different data center profiles. With compute infrastructure, again, thinking about what we need to deliver for those customers in this time frame, looking at, again, kind of 5-10 years and how those requirements would increase. So we've come up with, again, kind of 2 different approaches to the infrastructure. Both leverage the same interconnect and the same software capabilities. That's slightly different than today's Cray's approach to delivering the software stacks and the Erie's interconnect. But we're delivering that in this time frame by having a dense compute option and a more standard rack type of configuration that can go into traditional data centers or colo facilities, et cetera, to really enable that level of flexibility. From the storage side of things, kind of the big difference here that we looked at is again, how do we increase the simplicity, lower the complexity, lower the cost, and also at the same time kind of delivered a tiered storage capability that will meet the needs for exascale. So that's what we've also done by, again, kind of leveraging the Slingshot interconnect to bring the storage directly onto the high-speed network to do that. So we've eliminated things like the LNet routers and other capabilities that you require in a traditional HPC environment today. And then finally, the software stack. So again, looking ahead, the future is very much unknown and what the software ecosystems are going to look like. If you look at just what's happened in the last few years around artificial intelligence and machine learning, there's been a very rapid evolution of the software environments. So we wanted to make sure that that software stack for the future was really built around that philosophy. So it's very modular, very extensible, and we're looking again at supporting, kind of also traditional distributions of software, et cetera, to really enable flexibility and choice and interoperability with a lot of existing data center environments today. Right.
Great, thank you very much. And then next we'll hear from Altair.
Do you have mine up there?
I'm not sure.
What's the forward? I think you put it
Down in the left-hand corner, I see it.
You see it? Lower left
right
corner.
down here in the bottom left.
Ah, there it is. Hey, I'm glad it's here. There you go, all set.
All right, Altair is an interesting company because we originated over 30 years ago from a group of engineers in the United States. Over 90% of us are really trying to innovate solutions, simulate them, and of course use high-performance computing to accomplish the task. So let me slip through here real quickly. Everybody might realize that Altair is known for PBS, which originated from NASA. And Altair purchased it almost 18 years ago. We've done a lot to it, but as you can see on the right-hand side here, PBS as a workload manager has been a very good tool. Had a lot of different features added to it, but most of the people that use it have to cost justify their HPC spend. And a lot of the information that we received today at the beginning of this session talked about how businesses are improving and how HPC is growing. So that's forcing Altair to try to provide all other types of functionalities to cost justify your HPC environment. So you can see on the bottom right-hand corner, we're being asked by companies to actually take an on-premise secure environment and push it into the cloud. That's a tough technology to accomplish because we have to interface and interoperate with other providers. There are many companies in this room today that we are partners with to accomplish that. You can see their remote visualization and being able to look at the data and be able to manage the data and control it. You can see on this picture that we actually have the ability to monitor your jobs through your cell phone, your smartphone. I don't know of any other cloud providers and workload management companies that enable you to do that. Analytics, of course, is very important. You have to justify what your spend is, and you have to make sure that you're monitoring the right metrics so that you know what your workload is and how it's being used on the system, and if you have the right resources to accomplish the task. And of course, because cross-domain security requirement inside of the cloud and on-premise and being able to control it is very critical. I had a conversation today with somebody who said, we don't go to the cloud. We understand that. So if you look at this slide, you'll know that right smack dab in the center, you'll see Altair PBS Pro or Professional. But we recently have acquired and are co-integrating some other technology that will allow us to be a great provider of workload management control and job sets and throughputs on the new exascale computers that are coming. We sit on some advisory councils and we're able to participate in a lot of the technology developments that we've heard discussed today. So you can see Altair Accelerator, that is a tool that will perform and execute jobs at nanosecond rates. You'll see an Altair Accelerator Plus beneath that will even do that faster. It really depends on what types of jobs you're running in your environment, what systems they're running on, and how quickly you need the data to be processed. Altair Access on the left, you'll see here with an engineer or a scientist, these are the grouping of tools that enable the engineers to just do their work. They don't have to be an IT manager. So on the far right, you'll see Altair Control. That deals with the HPC administrator and all of the tools that they would need to make sure that the systems and the resources are functioning as planned. So let me just go through here. We have just a minute and a half. This is a great summary slide of what the new PBS Work Suite looks like. We take care of workload management, but we also take care of advanced HPC usability so that people have access and you can control their access to the resources that you have in your environment. License monitoring and management, I don't know if you know this, but some of the most expensive things you'll pay for are software. I see heads going up and down like this. If you could track and know who was using what features, on what tokens, on what systems, you can manage your accounting much more credibly and accurately, and you can make sure that you can afford to spend the money where you need to. So we have a couple of tools that enable you to do that. They're live and you can manage them. Resource and dependency management, Flow Tracer and Hero, these are a couple of other tools. These are actually algorithmic programs that will trace the actual path of your job through your resources and tell you where it failed and why. And I don't know about you, but I always hear people say, why is my job not running? This will enable you to be able to do that and see exactly where that takes place. All right, thank you very much.
Great,
Appreciate
thank you very much. Next, we'll hear from DDC. And let me get that one slide up. There we go.
I'm Gavin Miller with ScaleMatrix DDC, and I want to talk about cooling some of these high-end systems that we've been talking about today. And whether there's been a lot of debate over Moore's Law, whether you believe it's dead, dying, or will last for years to come. What we do know is that as the density on the chips has increased, so is the heat that gets expelled from them as well. And cooling technology hasn't really kept up with that chip technology in the same way, and many reasons because it didn't have to. If you look at the mainframe computer rooms of the 60s, the technology really didn't change. As you look to these somewhat modern day infrastructures that have been built even within the last 10 years. You walk in, you see a raised floor environment, you've got perforated tiles, you've got air coming up through that, and that's used to cool everything in the data center. It's kind of like us buying a carton of milk, bringing it home, putting it on our kitchen counter, and then cranking our air conditioning to the point where we keep that carton of milk at the optimal temperature. So there's a lot of waste around that, and people looked at hot and cold aisle containment in order to do that, but really there needs to be a better way to cool that. Enter liquid cooling, and we've seen liquid immersion technologies where you put the rock on its side, dip it in a tank, and it's very effective, but a lot of people have been resistant to put that type of infrastructure and complexity into their data centers. And then we've seen liquid to the chip, we've seen rear door chillers, but what we're seeing today is people that have implemented those types of technologies that are still having issues as the workload densities increase. So we've taken a different approach. We've basically, if you look at our systems on the far end of that slide, the first thing you'll notice is it's a container, it's a cabinet. We've taken the approach of putting that milk inside the refrigerator, and we manage the airflow within that cabinet. But the real difference is in the what we're calling the liquid air hybrid system that's in the head unit of that cabinet. And through that, we can control the flow of the liquid as well as the speed of fans, and we can dynamically alter the amount of cooling that gets into the cabinet. We do that very efficiently. The result is that you can see workloads of up to 52 kilowatts per cabinet. We do that at about a PUE of 1.15, and we're able to adequately cool these high-end systems that we're seeing. We were recently at the NVIDIA GTC show. That's the picture down in the corner. Jensen stopped by to see 3 of his DGX2s systems running with a NetApp flash array and a Cisco switch. That workload, approximately about 40 kilowatts in the rack, and we can cool that very efficiently. Obviously, we want to continue to push the limits of what we believe we can get into the cabinet, and we're working on that within the labs. But at the end of the day, we want to be able to take these systems. They perform better in our cabinets. They'll last longer, and overall increase your ROI as you look to implement these systems. So I'll be around. Would love to talk to you about how we approach these solutions and see if we can help you in your problems that you have with heating these dense systems.
Great, thank you very much. And then next we'll hear from IBM.
Okay.
Second year slides.
Kent Kinniger from IBM. I'm concentrating on unstructured data these days, and for AI, ML, and DL. And we've been working with the social media companies and the automated driving companies because they're driving lots of data very quickly, and they're giving lots of advice on what would work best here and there. And I'd like to share you, this seems to be a great topic because I think 3 or 4 or 5 people have spoken on it already. So it's what do you do to actually archive exabytes of data over decades is the question. So here's the problem for the car companies. If you look at how much data they collect per car and how many cars they have and how it adds up, they're looking at lots of exabytes per decade. Okay? And so they have to prepare to do that now. They have to have their systems so they don't have to change them several times along the way. They have to prepare for that now, and we've been working with them on that. So we've looked at, this is what they've been told, they've been telling us it needs to be simple, okay? Finding the data matters. I've heard several talks on that today. You really need to be able to find the data, okay? You need to retrieve it easily. Orders of magnitude matter. We're talking about different architectures have that. Exponential improvements, automation. This system needs to be fully automated. It needs to be touchless, right? Power, space, cooling are obviously a big problem. And then the risk of the technology matters, and that's a touchy subject, and that's where the social media companies have been helping us. And decade-long and activity. So activity means it needs to be active. The second law of thermodynamics does apply over decades. So, okay. And so we're following the big girls and boys, okay? Social media, government, and the car companies, and they use lots of disks in lots of clouds. They archive lots of data on lots of disks and in clouds, and they archive lots of data on tapes. So I'm comparing that. IBM has already sold exascale clouds to companies, so cloud, on disks. So disks with, in clouds work really well. I'm going to explore the other side of what happens if you try to put it on tape. So I threw these numbers together very quickly at that table over there today because they moved me up one day on speaking. but I think they're accurate. So it turns out, whether you're on disk or tape, the throughput's really good, and the cost of increasing the throughput is not a big percentage of the total media. For latency, if you're on disk, you get sub-second latency. On tape, you get about a minute. Now, if you're retrieving data that you stored 5 years ago, that makes no difference at all. For deployment, it's faster to deploy the tapes than it is the disks. They're actually quite much easier to install, installing lots and lots and lots of disks. For archive and recrawl, it's transparent on both. In fact, it's the same software on both. And so we go down here, but what gets interesting is when you get into the pricing. And so the price I'm looking at there, at 20 cents a gigabyte for cloud archiving is a real number. That's what customers are paying for it. But that's highly protected, multi-site protection, so you can have 3 or more sites you spread your data over, so it's extremely resilient data. For tape with the same similar protection, it's about 2 cents a gigabyte. So an order of magnitude there. And then if you look at the technology changes over the years, okay, they seem to be predicted to track so that the lines won't cross. Flash, disk, and tape will all continue to go down, and right now it doesn't look like those lines will cross for the next 10 years. But what's the what might happen? Well, in Flash, NAND has hit the end of its life, and there's a handful of things that are looking to replace it. Some are probably going to work. In disk, we have HAMR and MAMR, okay? And the disk companies say it's going to work well, but we know that when you scale something in production, bad things can happen. So those are brand new technologies. And in tape technologies, it's just going on and on and on and on, using the same thing until sometime in the middle of next decade, we'll see a whole new tape technology. IBM Labs has produced this. It's working in the lab. It's a 330 terabyte cartridge, which means I can hold 3 of those in my hand and have a petabyte in my hand. Okay, so that's already working. It'll take many years to make it into production. So, and then this is what we have for finding data. It's called Spectrum Discover. This will index data very quickly. You can access it, whether it's in our clouds, on our high-performance storage, across lots of NAS. It'll find it all. And it does deep searches, so you can look at all the data inside, not just the metadata. And this was developed specifically for auto companies to find their stuff. That's it.
Great. Thank you very much.